Hey everyone, Morgan here. So we're on page 3 of the AP Chem lecture outline dealing with bonding and Lewis dot structures. And we're going to look at some molecules today that are a little more complex. They're not just everybody's going to get an octet right away style. Now the first one here is going to be diatomic oxygen. Now I've got two oxygen atoms, each of which has 6 valence electrons. The only thing I can do to give all the oxygens, both of them, to give both the oxygens an octet is to take 2 of the electrons and put them between the atoms and put 2 lone pairs and then do the same thing on the other side. So now I have 1, 2, 3, 4, 5, 6, 7, 8 electrons associated with the oxygen on the left, and 1, 2, 3, 4, 5, 6, 7, 8 associated with the oxygen on the right. Okay, they both have an octet. If you're looking for some magic formula that you can just type some numbers into a calculator and figure out how many bonds are going to be in a compound, it doesn't exist. Sorry, this is, to a certain extent, trial and error. Now for C2H4, yesterday we looked at C2H6, and in C2H6 we had a single bond between the carbons and then 3 single bonds off of each carbon for the hydrogens. Now there's only 4 hydrogens. So 1, 2, 3, 4, each coming in with 1 valence electron. So the carbon has 4. It'll share 1 each with the hydrogens, that's 2, and then share 2 between the 2 carbons and form a double bond. Now, carbon dioxide is one of the trickier molecules. They ask this one a lot. Turns out that what you get will be double bonds to each oxygen and 2 lone pairs on each oxygen. So if we wanted to do a slightly different approach and count electrons, 6 valence plus 6 valence, that's 12, plus 4, that's 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All are there. Okay? Now for N2, diatomic nitrogen, it turns out we get a triple bond between the 2 nitrogens and then lone pairs on either side. For C2H2, we have our 2 carbons and our 2 hydrogens. The hydrogens each come in with 1 electron. Then 1 of the 4 from carbon goes to the hydrogen, and 3 go into the bond to the other carbon, and I get a triple bond. Okay. Carbon monoxide is a tricky one. Now, I'm going to color code. Let's start this over again, and let's color code. I'll do carbon in red. I will do the oxygen in blue. Now, the carbon has 4 valence electrons. So I'll put a lone pair out here, and then 2 of them there. Now the oxygen has 6. So here is 1, 2, 3, 4, 5, and 6. And I know that this structure bothers a lot of people because 2 of the electrons, these bottom 2, the way I've drawn it, are both coming from oxygen. Well, we had a name for that previously. We called that a coordinate covalent bond. That's allowed. It's not a big deal. Okay? So triple bond there. Now, here is how I would actually think of it. Nitrogen has 5 and 5, which is 10 valence electrons. Okay? It had triple bond. Okay? Carbon monoxide, 4 from the carbon, 6 from the oxygen, that's 10. That's the same as N2. It's going to have that same structure. Okay. Now, for HCN. When we have more than two atoms, we typically put them in the order they're written. So an H, a C, and an N. 5 plus 4 is 9, plus 1 more is 10. It looks like we're going to have a triple bond between the carbon and the nitrogen, and a single bond to the hydrogen with a lone pair out there on the nitrogen. Okay. C2Cl4 is the same as C2H4. 2 carbons means we're going to have a double bond here between them. Now, the chlorines, as I have said before, halogens only form single bonds typically. There are some exceptions. We'll talk about them later. So I'll put the 7 electrons around each of the chlorines. And then the carbons, what happened with them? Well, I used 2 electrons to make the double bond. I'll use the other 2 to bond to the chlorines. Now please remember we are doing these all as Lewis dot structures, which means they are going to be dots and not lines. COCl2. Put carbon in the middle. Now I'm going to put an oxygen up here in blue. I'll put some chlorines on either side. Now the chlorines, like I've said, halogens, single bonds, easy to work with. There we go. Now, carbon has 4. I'll put 1 there and 1 there. Now, most likely what we're going to see is 2 of those are going to go right here. Those were the last 2. And then the oxygen will have 2 that it donates right there, forms a double bond, and then we have 2 lone pairs on that oxygen. Now, all of these had multiple bonds, at least at some place in the molecule, but they all followed the rules. Everybody ended up with an octet, except the hydrogens, which are quite stable, with a duet. Now we're going to look at some molecules that behave differently because they can hold more or less than 8 electrons. PCl5, phosphorus in the middle, happens to have 5 valence electrons. Well, that's interesting because there are 5 chlorines there. Maybe this is a chemical conspiracy, or maybe it's just that's the way it happens. It'll share 1 of its electrons with phosphorus. Chlorine, 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 and they're all going to do the same thing. Have 3 lone pairs and share 1 electron with the phosphorus. Now, your first thought is, what's the big deal? That's fine. Well, the big deal is that phosphorus has 2, 4, 6, 8, 10 electrons around it. That is allowed because we have d orbitals available on phosphorus. Anything that is in period 3 or lower. And period 3, you know, it starts with sodium and goes all the way over there to argon. If you're in period 3 or lower, that element is capable of seeing more than 8 electrons. Doesn't mean it's going to, it's capable of it. Now, Xe, which does actually form a few compounds. Linus Pauling did it at Caltech back in the 1930s or 40s. And the 2 fluorines. Now, the fluorines are boring in a sense. They only form single bonds. We know what they're going to do right away. Now, the xenon's got 8 valence electrons. I'll put 1 there to form a bond, and I'll put 1 there to form a bond. 8 take away 2 is 6. The remaining 6 are going to go on to the xenon as 3 lone pairs. Okay? No double bonding. Xenon might see 10, but that's fine. It's got d orbitals. SF4. I'm going to put sulfur in the middle. The fluorines, once again, are very easy. Actually, when you see halogens in a compound, you're going to know how the bonding's going to go. So they're easy to deal with. Single bonds. Of course, there is an exception I'll show you later on in the chapter. Kind of an important one, but in general, we can say single bonds only for the halogens. And now I've put 7 on each of those fluorines. Sulfur has 6. So I put 1, that's 2, that's 3, that's 4 electrons I've used. I've still got 2 more. I will add them onto the sulfur as a lone pair. And I think I'm going to circle that just to make it kind of obvious. That doesn't mean you have to do that, okay? It's just something that makes it obvious to see. All right. I3 minus. I'm going to do a central I in red. And then here on the opposite sides of it, I'm going to put the other 2 iodines. And I'll treat those as halogens, because they are, and I'll give them 7 valence electrons, and there's 7. They only form single bonds. Now, the iodine that's in the middle, I can add 1 electron there, and 1 electron there. Now, iodine typically comes in with 7. The minus sign gives me an extra one. That's 8. So 8 take away 2 is 6. And you know, this is behaving just like another molecule that we saw up here, XeF2. 3 lone pairs on that central iodine. All right. Now, BeH2. Beryllium, 2 valence electrons. Hydrogen each coming in with 1. Sharing them. Beryllium is seen less than an octet, and that's acceptable. Elements in group 2 and elements in group 3 quite often will form bonding with other elements that doesn't satisfy the octet rule. Okay? Now they're very reactive, would readily accept more electrons, okay? But it's stable with just those 4. Okay. The PBr5, well, that's just the same thing as the PCl5, okay? Let's look at SF6. Sulfur in the middle. Now, I've got 6 fluorines. Each one of them coming in with 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And it's just going to be single bonds because they're halogens and very predictable. Now, the sulfur has 6 valence electrons, 1 for each of those fluorines. That sulfur is surrounded by 12 electrons, and that's cool. It's got the d orbitals that can hold them. In a rare case, we even get up to 14 electrons. BF3, boron, is in group number 3 or 13, which method you use to label the periodic table. So I know the fluorines are not going to double bond. It was a mistake Morgan made on a freshman chem exam years and years ago. Those 3 open electrons will each take 1 from boron, which has 3, and there we go. It's not 8 on the boron, but it's still pretty good. Okay. Now, C6H6. I throw this in here just so you can see it. Okay? It's the first ring structure that we really talked about a lot in chemistry, and so many things are based on our ideas for it. Now, I'm going to do the hydrogens first, because the hydrogens come in each with 1 electron. Now, carbon, each one has 4. 1 is going to go to the hydrogens. Got to form that bond. That leaves 3. One on this side and one on this side to form a bond to the other carbons. And I'll do that all the way around. Meaning that now what I've got is one more electron for each hydrogen. Well, right here, I'm going to give it a double bond. Now those are complete. So down here, I'll give it a double bond, completed the octets, okay? And then over here, I'll give it a double bond and complete the octets. So we have alternating single and double bonds for that structure. Okay, that is page 3 of this outline. Practice, practice, and practice. And then in our next video, we'll look at page number 4.